Hi, welcome to the final lesson in our quantum computing course. I was excited to get here to the variational quantum algorithms. This is exciting and one of the most exciting and practical algorithms that is used in today's quantum computers. Here I leave you the installation requirements and the libraries. I just specify this class that we're going to use as a wrapper to match the expected interfaces that we're going to use after this. Um, Here, what's a variational quantum algorithm? As explained here, um, you uh, can think of it as a hybrid quantum classical algorithm that use parameterized quantum circuits to prepare quantum states. This is combined with classical optimization with a classical computer to find optimal parameters. In the noisy intermediate scale quantum devices is one of the most promising approaches for achieving quantum advantage on the near term. Uh, here I'll leave you some of the core components summarizing that. Think of it as you have some parameters on the quantum space. Exploring it, when you measure it, you use the classical approach to update those parameters. In the mathematical framework, you can have this parameterized quantum state as C in function of the theta that we want to minimize. And this variational part is what we mention as, we mention here as, just correcting this one. We mention here as due to this minimization, this optimization, we call it variational approach. H is gonna be the energy on the system, and the energy is going to be minimized through this approach. We get then the variational quantum algorithms. What makes them special? Throughout this course, we've learned quantum gates, entanglement, error correction. But here's the reality: quantum computers are noisy, so they can only run short circuits before the coherence destroys our quantum information. We saw some strategies in the previous modules to mitigate noise or somehow approach error correction with logical qubits, but sometimes this is not enough, and VQA solves this with a hybrid approach. Quantum computers prepares special quantum states using short and parameterized circuits, and classical computers optimize the parameters by measuring the results and calculating improvements. If you think it in a iterative loop, quantum and classical work together, they're going to get better in each iteration. And the key insight here is that instead of running one long, deep quantum circuit that fails due to noise, we run many short quantum circuits. And using the classical optimization, we can guide the circuit, the parameters toward the most optimized answer. As any optimization problem, it's never like the exact answer, but the closest correct answer. So think of it like this. In the old approach, you try to solve the entire problem with the quantum computer, but with the VQA approach, quantum computer explores the solution space. It tries to give you an idea of what you have, and the classical computer navigates them. So this makes VQE noise resilient and practically practical on today's noise intermediate scale quantum devices. The two main VQEs that we'll implement are variational quantum eigensolver and quantum approximate optimization algorithms. So, checking here the implementation, for this eigensolver, we're going to recreate the Hamiltonian and the ansatz. We're going to use the previous workflow. So check that this H2 is the Hamiltonian code. This is the classical. It's a hydrogen. This H2 is the is going to be related to the Hamiltonian of the hydrogen molecule. This is the classic quantum chemistry test case. We're going to set some of the terms related to this Hamiltonian. Understanding this Hamiltonian is that after applying the something called Jordan-Wagner transformation, we map the hydrogen molecules into electrons onto two qubits. So each term represents interactions. Here the first one is the energy offset of the constant energy shift. The set Y is the energy offset of the electron on orbital 0. Well, for being clear, I'm going to write it down. Identity term, this is going to be energy offset. It's a constant energy shift. In this one, this is related to electron on orbital 0. This is the energy estimated in electron on orbital 1. This interaction is interaction between the electrons. Notice that's why it's double slit between electrons. And here I got a quantum exchange terms that are purely quantum mechanical. For here, you don't need to understand this more than is these values are from chemistry calculation. These are the exact energies for the hydrogen molecule at a specific bond length, which are already transformed from our orbital molecules to qubit operators. So this part is easier if you just assume it at this point. But then the ansatz, remember that in any optimization you need an ansatz. So you're going to trial a wave function and try to minimize it to the lowest energy. And this is, please don't, this can be complicated, but please don't lose it. Remember that here in this class, we're going to create a variational quantum eigensolver, where we're going to use these real amplitudes. We're going to set it to 2 qubits, and we need to repeat the circuit structure two times for more expressivity. So this creates in total 6 parameters that we'll optimize. And why this ansatz? Because it's a good balance. We have expressive enough so we can represent many different quantum states. It's shallow enough, only depth 1, so noise doesn't destroy it, and it's hardware efficient. Use native gates on real quantum processors. So this is like enough. And then in the implementation here, what we are sorting in this class, we have the Hamiltonian, which is the operator of the hydrogen molecule we define. We have the ansatz with it's our parameterized circuit, and the shots, the times that we're going to measure it. And the more shots, better statistics. Then we have the optimizer's map that is going to get these definitions, this string. We have the optimizer map get to optimizer name and SPSA. This is simultaneous perturbation stochastic approximation. It's a gradient-free, noise-resistant method which is good for quantum. All of these are techniques from optimization. We're going to use these ones because they are the ones with fast convergence and handless constraints, but this can vary depending on the situation. Right now, for the noisy quantum hardware, a gradient-free method works best because gradient estimation is unreliable with measurement noise. We're going to also to set the simulator with AR estimator and just define a number of shots as a variable here. In the optimization story, here you're just going to store the values of the on how is going to evolve our system, so we can visualize the convergence later. And the cost function is going to be defined here as this method. You're going to have this bound, which is based on the answer that you have, and you assign the parameters. The parameters are gonna be an array of rotation angles, and you're going to assign the parameters with these angles into our answer circuits is initial, and the decomposed part it breaks down high-level gates into hardware native gates, right? Why decompose in Qiskit? Remember that we use real amplitude as an abstract template, so we need to convert it to actual gates, rotation operations and C-node operations that the simulators or the real hardware can execute. So that's how we can transform this into the simulator language or the quantum computer hardware. And just you can have your optimized method. The optimized method is going to initialize these parameters as none, and here you start the VQE optimization. In the initial parameter, you're going to, if not provided, use random initialization. Random angles goes from 0 to 2 pi, and why random? Because we don't know the answer, so a starting point doesn't matter much for VQE. Imagine that you have any numerical method, you just set some random value to start. And this is the result going to use this optimizer minimization of the cost function that you have here previously defined with the initial parameters. Then what you want to check is the parameters and also the optimal energy, right? The optimal parameters are going to give us the optimal energy, which comes from fun, right? Being fun, the result, the method from result in this optimizer. Remember, we have this as the minimization of the energy of the system. And fun is the cost function that we defined previously. And here is where the hybrid magic happens. The optimizer calls the cost function repeatedly, and each time running a quantum circuit until energy stops improving. So in results X, you're going to get the best parameters found, and here you're going to get the best energy achieved for the system, plus the follow history for analysis. And mainly that's it. Here I just print the results, and you just I add this method so you can get the optimal state too. For the VQE demonstration, you can just set it here and check the results on how the energy is converging. There's some analysis on how it's looking the circuit. Here you get some of the iterations. Going to the end, optimization is complete with the final energy minus 0.1, minus 1.9. The convergence was found in the total in 172 iteration that the success was true. You can check it moving parameters or moving the energies, but take into account that at different energies maybe you cannot find a solution and this could not converge, which is not ideal. Yeah, so let's continue with the check here with the exact ground state of for our Hamiltonian. The VQ energy was minus 1.9, but according to literature it was 1.8, the value that we were supposed to get. Here the error is miscalculated. Oh yeah, no. Here we're considering the error from the energy that we estimate from the VQA results and the true exact energy from the eigenvalues that we define a lot of matrices there. So estimating them, we could check the real value. If we want to check it with the literature, which is this one that is reported, let's just run it here as this one, and then you have this error correction. But in this case, that's not the ideal case. We have 0 here. Sorry, this should be abs of this. But yeah, the VQE here error, it's 0 because it means that we reach a good optimization of the eigenvalues of the system. Remember that these eigenvalues, we know it because this is a small system, but if you get a more complicated system, maybe it's not easy to estimate. Remember that at the end, this is just the scheme that you're following, initialize parameters, you do a quantum circuit, you do the measurement, then you do the cost function, that's gonna be solved by the optimizer, but it's gonna be a classical optimizer, and you just create a loop until you optimize that part from that measurement. At the end, the first part acts as a dynamic circuit if you want to see it, because at the end you have a classical circuit, but the whole concept you can see it as a dynamic circuit. Everything goes from the measurement point, and you just can use several shots then to optimize this part. And well, that's what this part of the code is gonna do. I'm gonna also leave you another method with each quantum approximate optimization algorithm. To not make this video too long, you can check it, but you're also going to have the code here. I wanted just to add that I added here the advanced visualization of the VQE results. I'm gonna upload this version 2 with the repository. Here is just to observe the convergence plot from the different iterations, which is going to show you just how the energy is minimized on some step, and you can plot this information as anything you want to, depending on your system. Then I'm just gonna leave you some takeaways from this part, where you have some applications, some fundamentals, and problems that you could look for it if you want to check it. But the main basis is the scheme that we discussed. Just set the parameters, do your first part of the circuit, and then define a cost function with an optimizer of those models in every cycle. Thank you so much for being part of this course. Is trying to do it short and concise and something useful that you can approach, which are hard concepts, in a fast way. Of course, everything it's more easy to understand if you study it from other courses specified just on quantum computing or quantum physics, and then using these libraries and these applications. But sometimes you need particular applications, and that is why I decided to do it this way. You can come to check Qiskit for a interesting way to see what's real quantum computing, and that's why it's important, the inclusion of the noise and how to deal with it. And this is something that I consider is fundamental for the expressivity of the quantum computing and the real challenges that you can face. And thank you. You can, as an exercise, try to look for new libraries, to look for new technologies, and also implement all of these exercises in another version using the different libraries. Thank you so much, and thank you for coming here for the future of the quantum computing. See you maybe in another course. Thanks.